其他人，其他人，其他人啊？A lot of you went back for holiday, so quite a few of you didn't. It's not here. And how about the rest? Deal. Rushing for deal? Yeah. So I have a suggestion for you guys, right? So since you have so many work done, I guess you might want to work more efficiently. So if you're stuck on some problem, right? See how long do you take to solve that problem, and then learn from there. How can you improve? Okay, don't just dive into problem and then solve it. Huh? What? You? Huh? Yeah. Same. I mean, similar. It's similar. So it's similar. So whenever you have a problem, you are not just solving it, but see if you can solve faster. Okay. I mean, this is what exam bring to you, right? Exam always have time limit. Okay. So yeah, try and learn from each time. As that some of you like enjoy diving into your problem. So like you just stay inside the problem for quite a long time. So try to reduce the time you use. Okay. Uh, any question from previous lecture? Hmm? Previous lecture. Have you tried all the homework question, tutorial question? Yeah. Yeah. Please try it. If you have any problem, we can discuss together. Because I won't be around during the exam week. So if you have any question, please bring it this week or next week. Then we can discuss together. Okay. And I'm not sure yet whether your class need extra classes or not. Hopefully not. If we need, then maybe we need to discuss at some point. And because the other class we will be having extra class because they still have ODE apart from vector calculus, but we just left with vector calculus. Hopefully we can finish in 3 days. Okay. Okay. So let's do some recap. We have learned last time. So we last learned that work done. Okay. So in physics, what is work done? Physics work done is W equals to force time distance. Okay. So there are two things you need. So your force needs to be able to move some positive or negative displacement to get non-zero work done. Okay, so one is a force. The displacement. So displacement is a vector, so you have a direction, positive and negative. So direction is very important in this vector calculus topic here. Or sometimes we call it an orientation. Okay, orientation. So this is just one direction. Okay, one direction, forward or backward. But in vector calculus, we'll learn about work done as a integral of a dot product. Okay, dot product of two. So in vector calculus, and our work done is an integral. Integral along a path. Okay, you still move your particle along a path. Okay, but this path is a path in 3D. So you got vector here. So how do you obtain a function? Okay, so you just dot two vector together. One is the force, one is the curve in 3D. Okay, if you like, you also can put arrow on F to denote that F is a vector. Okay, so this is a dot product, right? Okay, so how we expand this dot product? Okay, so the way we expand it is using the parametrization. Okay, so we need to parametrize our curve into parameterized curve first. Okay, so we need to write, we need to parameterize curve C. Okay, maybe using a time variable. Okay, using a time variable. Okay, so we replace our variable into t, okay, maybe t1, t2. Substitute our f with our curve. Okay, see what happened along the curve, and then dot with the tangent vector. Okay, dot with the tangent vector. All right. So if you wonder what is RT here, so we replace our C by RT. Write it better. This our C is RT. Okay, and then RT. So to define a vector function, okay, what do you need? So if this is in R3, so let's say, suppose this is in R3. So how many coordinate you need for a vector function in R3? Huh? How many coordinate you need in R3? Tishon? 3, okay? So you need to explain your x in t, y in t, and z in t. So I give you a t, you need to give me a position in the space. Okay, x t, y t, z t. And then from here, you can see that these positions are changing with time. Okay, so they are changing with time. So you can take the derivative. So how to take the derivative of a vector function? Grace, how to take derivative of vector function? Yes, okay, do it component-wise. So you need to differentiate component-wise. Very good. Okay, so this is the R prime t. Okay. So so first we can write our function into 3 components as well. Okay, so let me move here a bit. So what is our f? So our f here will be given by f1, f2, f3. Okay, so let's say we fix ourselves in R3. Okay, so in this case here, we got f1 x in t, f2 x in t, sorry, y. Wait. Okay, maybe I don't want. Okay, let's write it down here. So xt, yt, zt. Okay, then this vector is kind of long, so let me just write them out. F1 zt, xt, yt, zt, and f3 xt. So let me move this down. Size Okay, so your first function need to dot with your tangent vector. Okay, what's your tangent vector here? So your tangent vector here, we could write it as we write it as so you can write it as x dt, and the other form dy dt and dz. Okay, does it make sense or not? So your force is a vector. Okay, your curve is also a vector. So I got 2 vectors here. Does it make sense? Okay. So far okay or not? Okay. Force evaluated at the point. Okay, so you can see that there's what? There's composite of function here, right? Okay, because force first is defined using position in XYZ. But this position we can explain using a parameterized curve. Okay, parametric equations. So we explain XYZ in terms of T again. Okay, so there's some composite of function going on here. Make sense? Yeah, Sony, a question? No. Okay, yeah. All right. So do dot product. Okay, so if you do dot product, what do you have? Yeah, you have, for example, f xt, yt, zt on dx, dt. Okay, and then similar term. Yeah, I don't want to repeat writing the whole thing, so I throw away the point. Okay, so you can see that this reduced just to or maybe I need to change x1, x2 maybe. So you can see that we can swap the inter yeah time vector. So I confuse you. So I mean I should put like this. Okay, let me put like this. So this is what we define as the line integral with respect to x, y, z. Okay. Okay. So last time Ming you asked about what's the geometric interpretation of line integral with respect to x, y, z. Okay, so here is the motivation for it. Okay, so you dot product with the tangent vector. Okay, then you split up integral with respect to different coordinate. Okay, then we study one of them. Okay, each one of them. Okay, so this is the motivation we have for the line integral with respect to different coordinate. Okay, yeah, so this is definition. So when I put dot dot equal, right? So this is definition. When I put equal, this is equal. Okay, what do I mean by equal? Meaning the left side and the right side are already defined. I just want to show they are the same. Okay, but when I put dot dot equal, meaning so if I say, so if A dot dot equals to B, I means then A is defined by B. Okay, so meaning you don't know about A, okay, but you should know about B, then I define A to be B. Yeah, so this is the definition of line integral with respect to different coordinate. Okay, you just think, remember the word done dot product inside the. Okay, is it okay or not? Yeah. Okay. Okay. Next. Next is the fundamental theorem for lines integrals. Okay. So if you integrate a gradient, what you get is just you take the antiderivative of the gradient, okay, at m point, and then take the difference. So does this remind you anything or not? In the calculus of one variable, right? You learn fundamental of calculus. What's the fundamental theorem of calculus? So if f is the antiderivative of, okay, so if big F is the okay, so if the big F is the antiderivative of small f, okay, then if you integrate uh, f from a to b dx, it is just capital FB minus f. Okay, so this is not immediate, right? This is not immediate because integral is defined using limit and sum. Okay, so you need to prove this. So they call it a fundamental theorem of calculus. Okay, so in higher dimensional, you should expect, okay, or guess that a similar things will work. Okay, so the thing, the derivative here, we refer to the gradient of f. Okay, we refer to the gradient of f. So let's quickly see why is this true. Okay, so because you see, so here is equal, okay, meaning both sides are already defined, right? So you can start either way. Okay, so the easiest way I think is start from the left hand side. Okay, we start from the left hand side. So what's the integral of a of a gradient dot product with dr? What is this? What's this? Just now we started with what? We started class with what? Word done. Okay, right, word done. So del f is a vector field. Okay, and then dr is another vector. So you integrate a vector field dot with a vector, you get a word done. Okay, so here is the word done expression here. Word done by a gradient of f. So word done. So how to compute this word done here? Okay, so your t. So we need to change everything to t now. Okay, so this is integrating from where to where? What's the range of t? From where to where? This curve is going from where to where? Huh? A to B. Okay, so you're going from A to B for this curve. So what is del f here? What is del f? Michelle, what is del F? Nebula F, sorry. Gradient of F in this case. What's the definition of nebula of F? How to find a gradient of a function? Any idea? Forgot already. Last chapter. What's nebula of F? Shunling, what's nebula of F? Gradient of a function. What's it? What did we learn in last chapter? What did we learn in last chapter? Partial derivative. Okay. Then what is del F? Somehow have to do with partial derivative, right? So this is a function in where? So this is a function in three-dimensional. Okay, so this is the scalar field from R3 to R. Okay, so what's the gradient of this function here? Yanbo, what's the gradient of this function? Huh? The gradient of F. What's the formula? What's the definition? Uh, X. Yeah. D dx dr. Ah, okay. Not quite, not quite. Okay. So R is a function. So here R is a function, and then R is a function of t. So let's write it here. R is a function of t. So you're suggesting that x is a function of R, if you are right like this. But what does it have to do with f? Huh? Respect to t? Not quite. So, I mean, you should imagine an example of f, right? Okay. How does this f look like? So, for example, you can imagine object x squared plus y squared plus z squared. So, what is del f? Yeah, 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 right. Okay. So, gradient of f is just del f over uh, del f over del y, del f over del z, right? Okay, so you see, so this is a very good example that you are just solving question. You don't know what you are solving. Because once you see similar question, hey, that definition sure will pop up. Okay. So what I want you to learn from mathematics class is you need to learn from definition. Okay, you need to learn from definition. Okay. So this del f here doesn't depend on any f you give. Okay, every del f looks like this. Okay, so you plug different f into this formula, you will get different gradient. Okay. Okay. So another thing, very important things to learn from the conversation just now is every time you learn this abstract definition, right? Make sure you have one example in your mind. When I say a function from R3 to R, so what does it mean? So you need to have a real function inside your mind to talk about. Okay? You need to keep some example inside your mind. So that this definition will make sense to you every time. Does it make sense? Okay. Okay. So here is del f over del x, del f over del y, and del f over del z. Okay, so I mean, maybe you confused because I haven't substitute my t yet. So maybe let me substitute my t first. This is the first definition here. So this is defined like this. I cannot set define, so equal first. Okay, dot with just now we already learned how to find the unit, the tangent vector of a curve. Okay. Okay. So what's this actually? What's this whole thing here? Del f over del x, dx over dt, plus del f over del y, dy over dt, plus del f over del z, dz over dt. Do you feel familiar about this expression here? Chain rule. Okay. Chain rule. So chain rule on what function? F with respect to t. Very good. F with respect to d. Okay. So if you differentiate your f with respect to t, then you'll get this whole expression here. Okay. So, but your f is in terms of x, y, z first, right? So in terms of r, t. Okay. So this is the chain rule. Okay. From here, can you see anything or not? What is this? Variable. Differentiating a derivative. What's this? Fundamental theorem of calculus. Okay, you return to one variable case. So you can apply the fundamental theorem of calculus. Okay, so this part is chain rule. Then the next part is fundamental theorem of calculus. I put FTC here. So what is this? So this is just the endpoint minus the starting point, the value at endpoint minus the value of start. Okay. Any question on this proof? Any question on this proof? Okay. So you see, this proof is also telling you that we solve a line integral inside 3D. Okay. But once we parameterize it, we are solving it in 1D. Okay. Although the line is in 3D, but that line we can parameterize it and then solve in 3D. Sorry, 1D, one dimensional. Okay. You just use time to control the position. Okay. Question? No? Okay, if you have any question, just feel free to stop me. Okay, next. So we try to example calculate this integral, line integral for this vector field. What's this vector field? Anyone remember or not? R over R cubed minus C, some constant C. What's this? Remember? What's this? Sorry. Gravity. Okay, so if you replace C with proper constant, you get the gravity. Okay, so this means what? What have we shown something on this or not? Let's see here. It's the conservative stuff. Yeah. Okay. So you see here. So we have seen that this function here, okay, is the gradient of this potential function c over square root x squared plus y squared plus x squared. Okay. So this is a conservative vector field, meaning that it is a gradient of some potential function. Okay, which is this. This is what we shown last time. Okay, so later we will integrate a line integral of this gravitational force field. All right. So see from so let me write down from previous example. Okay, we know that F is a conservative vector field. Okay, what does it mean by conservative vector field? Ellie. Don't know. It's a gradient of some scalar field. Okay, gradient of some scalar field. Okay. So that is, we can write F, okay, equals to gradients for some F, where in this case here, F is equal to C over square root x squared plus y squared plus x squared. Okay, this is what we have shown last time. Everyone okay or not? Okay, okay, okay. So in this case here, how do we compute this F here? Okay, this vector field here. So since it is conservative, we can rewrite it as a gradient of little f. Okay, gradient of the potential function. Okay, so what do you want to do from here? What can you do from here? Michelle, how do you compute from here? How do you compute a line integral? Formula? Which formula? Okay, so in this case here, because you are different integrating a gradient, you can use the fundamental theorem of line integral. Okay, meaning what? Meaning it is just f evaluate at the endpoint. Okay, so what's the endpoint here? So the starting point is 3, 4, 12, and then the endpoint is 2, 2, 0. Okay, so we take the endpoint, the value at endpoint, minus the value at the starting point. Okay. Where you just substitute your value in. So in the end, you get C times 1 over 2 square root 2 minus 1 over. Okay. So is there any other way to solve this question or not? Ming Xiu? Is there any other way to solve this question? Okay, so meaning using the definition. Okay, but if you do that, okay, you parameterize your curve. Is the curve given or not? Okay, so there's no curve different here, so you cannot do that. Okay, yeah, so you cannot do that because the curve is, they didn't tell you what's that curve. Okay, you cannot parameterize the curve, so you cannot use the definition. But if it happens that it gives you the definition, it happens that it describes the curve for you, you write down the parameterized equation, okay, and then you go through the whole process. What you get is also the same answer, because this is what my proof tell you. Okay, my proof start with any curve, any function. Okay, the end result is this two number, the difference of these two numbers. Okay, so this is the power of proof. Power of proving. Okay, once I prove it, I tell you, no matter how you do it, the end answer is this. Okay, so I want you to appreciate proof. Okay, of course, proof are hard. Okay, but every proof comes with an example. So if you want to understand the proof, make sure you can throw an example and then execute the proof. Yeah, so to understand proof, you need to start with example. Okay, throw any example into the proof. See the example will work through the proof. Okay. 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 Next. Okay, next we have this idea connected. So I found that this chapter and previous chapter is a bit can I say advanced? Yeah, a bit advanced. Okay. So we will touch a few concepts in topology. Okay, so last time we talked about open, closed, right? So now we will talk about this connected. So what do you mean by connected? What do you mean by connected to you? Connected. Why? What's so funny? What's connected? Why, Jimbo, what's connected? Ask Jimbo, what's connected? 2 points are joined with something. Okay, two things are joined with something. Okay, so this is uh, the idea we want to put into a set. So when we say one set is connected, meaning any 2 points, okay, any 2 points you pick, I can connect with a smooth curve, okay, piecewise smooth curve. So when we talk about this connected in different contexts, right, you need to be careful. Sometimes we just call this path connected, okay, because they are connected by path. We have more general connected definition for future. But for now, as long as it is path connected, then it is connected. Okay. So we can see some example here. Okay. So is this connected or not? Can you draw a piecewise smooth curve between 2 points or not? This red one, not the white one, the red one. Can you draw given two dots? Okay, 2 point. Oh, but the laser become white. Interesting. Oh, interesting. Okay, so if you put two dots here, can it join by smooth curve or not? Any 2 point I pick. Yeah, pick the corner one also. Can join or not? Yes, right. Okay. How about second one? This one for the pink region. If you pick any 2 point, can you join with a smooth curve or not? Yes. Okay. For example, let me pick this one and this one across this line here. Can I join or not? Okay. I cannot join here, but I can join all the way wrapping around this complement of this A, right? They call it A here. Oh, here is A. Complement of A. Okay. So this is still connected. So is C connected or not? C obviously connected, right? Because I add more possible way because I removed this line already. How about D? Is D connected or not? Okay. So you can see that the orange part is connected. But how about this white part? Are they connected or not? No. Okay, because if I pick this and this point, there's no path I can to join these 2 points together. Okay, so there are four disjoint set inside D. Okay, so inside here is not connected. And so this is the next example, E1, E2, E3, E4. So this is not a connected set. Because if you pick a point from E1, pick a point from other E, there's no path you can find to join them. Make sense? Yeah. So far good. So far so good. Right? Okay. Next, a curve is called closed if its terminal point coincide with its limit point. So this is about curve close. Okay, last time we talked about a set close. Okay, now it's a curve close. It's a different thing, right? Okay, so this is a curve. But curve is also a set. And so you might want to think any relation between these two definitions. Okay. So you actually can see that a curve, right? What's the boundary of a curve? is actually endpoint, okay? Points. But you can see that. Can you find a point or not? There's no boundary for this. And there's no boundary for this. So it's A is closed. Okay? Yeah. So try and think whether the two definitions have connection or not. Because curve is also a set of points. So it's a set in particular. Okay. Okay, next definition. So the line integral of this word done, okay, the word done line integral is said to be independent of path in a connected set. Okay, if for any 2 points A, B, and D, the line integral has the same value for every path from A to B. Okay, so last time we see that actually the line integral depend on path, right? Do you still remember the example last time? You still remember or not? Yeah, so this example here. Okay, so we have 2 points here, okay, but connected by 2 paths. Okay, and then this is what? This is R2. Okay, this is R2. So R2 is connected or not? R2 connected? Any hole inside R2 or not? No, right? Okay, so R2 is connected. Okay. Sometimes we say, we didn't say so. So R2 is connected. Okay, so there's 2 paths here. Okay, so there's 2 paths here. So these 2 paths here evaluate to different value. One is -5/6, one is 245/6. Okay, so depend on path. But just now we gave a definition that let's say this integral is independent of path. What does it mean? That means no matter what path I pick, okay, I evaluate my line integral, I still get the same result. Okay, so this is what I mean by the line integral is independent of path. Okay, so what path I input to my line integral, I get the same result. Okay. Can you see why we have this definition or not? Remember what I did before introducing this definition? What do I do before introducing this definition here? What do I do? What did I did just now before introducing the definition of independent of path? Huh? Don't know? Forgot already. Yongzi? Oh, close curve. Okay, before that, before that, even before that, fundamental theorem of line integral. Okay, so does this fundamental theorem of line integral, the result depend on path or not? Does it depend on path? The statement. Does it depend on path or not? Does this statement depend on path? No, right? Okay, so you see the result here doesn't depend on path. Okay, but the condition is what? The vector field you integrate over is a gradient of some scalar field. Okay. Okay. Okay, so we got the result here. So we got the theorem here. Okay, before reaching that theorem, we will keep it for a while first. So let's do this theorem here. How about I just tell you? Okay, maybe I just tell you. Okay, so there's an independent path theorem we will see later. Okay, so let's say our F is continuous on an open connected set. Okay, open we have this shown in class. Right, close is proof in definition. Okay, open we shown in class. So open connected set. Then the line integral is independent of path if and only if your vector field is conservative. Okay, if and only if your vector field is conservative. So there are two directions here. Okay, which direction we have already seen? So if it is independent of path, then it is conservative. If it is conservative, then the integral is doesn't depend on path. So which direction will they see? What do you think? Let me write down the short line. So the line integral, okay, independent of path, independent of path, if and only if it is conservative. Okay, so one, the second one is two. So which direction will this in? What do you think? Which direction is given by the fundamental theorem of line integral? 2, 1. Okay, 2 to 1, because we start with f is a gradient of some function. Okay, but if you are gradient of some function, right, how do you compute the line integral YU? Yeah. Mhm. Okay, use the chain rule. So what's the result? There's a chain rule inside the proof. Okay. Ah, what's the result? Differentiate a gradient. Okay, you should remind yourself as a fundamental of calculus. Differentiate a, integrate a derivative. What do you get? You need to always remember the basic one, fundamental theorem of calculus. Integrate a derivative. What do you get? You get the antiderivative. Okay, evaluated at the endpoint, and then take the difference. Okay, take the difference where the antiderivative evaluated at the endpoint. Okay, so this is what. So this is just f at the endpoint. Maybe I call it R2 minus f R T1. Okay, where RT is going from T1 to yeah. Okay or not? Okay. So you can see that this is independent of path. Right? I only care about endpoint. I only care about endpoint. There's no path in this calculation here. Okay. So no matter what path you give me RT, okay, what I care about is RT1 and RT2. These are 2 points. Only 2 points. Okay, starting point and ending point. So let me label here. So this is the start point. This is the end point. Okay. Okay. So there's no path involved here. Make sense or not? Hmm? Question? No? Okay. Not okay. Where is not okay? Which part is not okay? Which part can you understand? Where do you start? Which line you start? If you don't understand, I think most of them don't understand. So where you start? What means you what happened? Not stuck. I mean he's stuck. is stuck. Where do you stuck? You don't know. Okay, that one I cannot help you. You find where you stuck and then you try and ask. Okay. Yeah. Okay. So we still need the other direction. Question? No question. What is independent of path? What is independent of path? You mean definition of independent of path? Yeah. So this is the definition. So you need to follow back. What is independent of path? Okay. So this property is referred to who? Okay. So in mathematics, right, there are two things you need to differentiate. One is object, one is adjective. Okay. Adjective must work with an object. Okay. When I say independent of path, this is object or adjective. Adjective. Okay. So to use an adjective, you need an object to start with. So who is independent of path? Okay. The line integral is independent of path. Okay. Okay. Let me teach you how to read definition. Okay. So here is the object. Okay. This one is the object. This is the adjective. Okay. So we got an object with an adjective. So what does it mean? Next. Okay. So what does it mean? You need to read after if. Okay. If will tell you what happened. Okay. If will tell you what happened. So let's read what is if. If for any 2 points A and B in D, the line integral has the same value for every path C from A to B in D. Okay. But you see, this after this if, they got A, B, D. A, B, D, right? So what's A, B, D? Okay. A, B is what? So you need to find the object. A, B is what? A, B are points. Okay. Points in where? In D. So now you need to ask, what is D? Okay, what is D? Yes, so D is a connected set. See, come again. Adjective and object. Adjective is connected. Object is set. So what's a set being connected? A set is connected if for any 2 points inside the set, you can draw a piecewise smooth curve between A and B, between 2 points. Okay. So why is this important? Because this line integral here, you need to integrate over a curve. Right? If you don't start with a connected set, you pick any random 2 point. Can you connect 2 point or not with a smooth curve? No, right? Okay. So in order for this line integral to make sense, you need to be able to draw curve, smooth curve in particular, piecewise smooth they allow, okay, between any 2 points. Okay, so you see, everything used inside the definition, right, must make sense. You cannot throw extra thing inside. I mean, it's not necessary. Okay, this is what each time I go through your project, I said this is not important, this is not important. I just scratch everything off. Because your main argument don't need it, then you don't need to put it down. Okay, we put the shortest definition as possible. Okay, so why connected? Because we want the line integral to make sense. And between any 2 points, I want to have a curve, I want to do line integral. Okay, line integral, you need a curve. Okay, so the line integral has the same value for every path. Okay, for every path. So there are quantifier here for any 2 points. So you pick any 2 points. Has any value for any path. Okay, you pick 2 points. No matter what path you draw, you get the same value. Okay, so this is very important. For any that exists, is different. That exists, you need to find one. For anything will work. Is it better understanding on this or not? Okay. So what do I mean by line integral that is independent of path? Meaning, for 2 points, I pick any path. Okay, I get the same value. Yeah. I take draw any graph, a curve, I take the lighter graph, I get the same value. I just can process. Okay. So yeah, okay. This definition first. Yeah.
So you mean smooth implies connect.
Smooth doesn't imply connected. Smooth doesn't imply connected. Okay. Smooth. Okay, so you see, this connector is defined on the set. Smooth is defined on the curve. Yeah, smooth is not connected. So smooth is okay, we haven't defined smooth yet, right? Okay, I mean to be precise, we should define what is smooth. Okay, so what's this smooth here? Okay, so this is a very good question actually. So this connector is defined by this after if, right? Okay. So after if here, do you know every word after if? You know every single word here or not? For any 2 points in D, okay, you know. Can join, roughly no, join only, right? Just join. Joined by a piecewise smooth curve lying entirely inside D. Okay, lying entirely inside D meaning is a subset of D. Okay, so this is a subset of D. But what is piecewise smooth curve here? Okay. I mean, we don't even have a proper definition of curve also. So, okay, so what's piecewise? Piecewise, do you know? Piecewise function. Okay, so you split your interval into different partition and then you define the function of it. I have piecewise. Smooth, what is smooth? So over this partition, the function is smooth. So what do you mean by a function is smooth? Uh, okay, depend on the degree of smoothness you want. Normally, when we talk about smooth, I think usually we talk it in the differential geometry sense. So smooth it means infinitely differentiable. Okay, so you can keep differentiating, so on. Okay, yeah, okay, infinitely many times differentiable. Let's keep this infinitely. I mean, the thing you saw also infinitely many times differentiable. Okay, infinitely many times differentiable. Okay, question. You mean the curve? Yeah, definitely. Because differentiable is stronger than continuous. Yeah. Yes, yes. So for example, like this. So like this, and then a king like this. So this point is not differentiable, but it is piecewise continuous. Piecewise different. Piecewise. Okay, so you can split it into the first part, the second part. Okay. Yeah. No, that doesn't define. That doesn't imply that because uh because no, that doesn't define. Wait. So you mean, you mean piecewise smooth curve does it allow discontinuous curve? Yeah, right. Yeah. I mean, isn't it? Yeah. So the continuity here is settled by this word join. You want to join, right? You cannot join 2 points using this curve, right? How to this one is continuous here. Okay. I mean, do you define this point or not? Okay, so this is not joint. I mean, so the continuity settled by the joint. Okay, if you really want to precise here, so this part here actually mean continuous curve. Okay, so if I really want to put this line into full mathematical definition, what should I do? Okay, what should I write? Okay, let me rephrase this definition for you. So we say that a set D is connected if for any 2 points in D, there exists a curve. Okay, there exists a con continuous piecewise smooth curve. Okay, with the initial point A and terminal point B. Okay, so this is a full, uh, precise mathematical definition. Okay, let me write it down for you. And let me show you something. Okay, so if I want to make this really precise mathematically, so a set D is connected if for any 2 points, call it AB, okay, in D, there exists, okay, you can find there exists a continuous piecewise, okay, so that means a continuous piecewise smooth curve lying, okay, yeah, so I could choose curve with starting point A and ending point B, lying, which, okay, lying entirely in D, okay, or which is a subset of D, okay, yeah, this is another way to say it. Okay, for 2 points, you can find a curve, continuous one, piecewise smooth one, okay, such that the starting point is A and the point is B. Okay. Yeah. Yeah.
So,
Yeah. Mm.
when that many independent join together.
That's the example of piecewise smooth curve. Piecewise smooth curve. But just now, because just now, Ning say this is also piecewise smooth, right? Yeah, this is true. This is also piecewise smooth, right? This is not continuous, but piecewise smooth. Because I just want piecewise is smooth. Every piece is smooth. Okay. So to avoid this example here, I want continuity. Okay. Yeah. Yes. Okay. Okay. Hope we have enough time. But I think this theorem is quite important for you. You guys can learn calculation yourself, right? Okay, never mind. I think I will try. Will try. Yeah, the concept is very important. Okay, maybe we take a break, a short break until 12:10. Then we come back. Okay. Yeah.
因为它所谓 independent 它就是你从这个是一个方，这个是一个方，你跑来这边去这边去这边去这边也是一个方，不是？它是在一个open set，不 full set 里面的。
哦，
如果你只是一个 curve 的话，就是只有两个 path，一个是这样，一个是这样。
对是
因为这个是一个 set 嘛，
啊，
然后你是讲 from point A to B 是这样子，你就这个是一个就很多种啊。
要多少？
如果那我只是讲我要一个 curve 啊，就是 close curve 啊这个吧，所以 from A to B 就只有这样子跟这样子吧，对吧？是这样是。close curve 的话，中间不算不是？
没有 close curve 只是一个 curve 在一个 set 里面罢了。OK，close curve 只是一堆 point 在 set 里面吧，没有什么东西。我都没说，
一堆堆在这啊。
就是 close，我不是 take 这个 close path as 一整个 B，你知道？
哦，所以
它是活在，它只是一个 subset of
所以
B。
curve 的定义是它只是一个在地里面的一个什么吧？
嗯，definition of curve 吧。
嗯，
嗯嗯
因为我刚才因为我的意思，
嗯
然后
嗯
最后开这 part 就是讲，如果是 conservative，不管你从哪里的，
我觉得要做的
它的都是一样的。
嗯，这样也比较好。需要已经是 continuous 了，如果是课，
我现在这样子找不到啊，因为我觉得你这样子
那
你要看你那个人，你说策划找不到这个人是
你这个 setting 的话是，这 setting 是不要拿太多这样的字了。
我觉得你这个不要谈了，还是我意思是讲，
你要讲吗？
因为我是要拿这个来所谓的那个 path，
嗯
所以如果我讲现在呃，那就是
哼
这一条线嘛，
嗯
全部东西没有了，
哼
所以我 pass from A to B 就这个跟这个吧，
耶呀，这样就可以了。已经包 condition 了是吗？
这个只有 conservative 的时候才 true 吧，就是讲 conservative 待会你们的
嗯，
就我要上到哪里？上完加油。
让你们来 AIT 上课，一次过教，怎么不要？怎么不要？这样懒惰的。OK 啦，OK 啦，不懂，我还不知道，还不知道。一下午有一堂课，我想一下，可能你们可以来，但是那个班上不够大，那可能速度会全部都一样去。再看吗？我不懂。Hello, testing, 1 2. Okay, so let's come back. Come back here. Okay. So what's the why we introduced independent of path and closed curve just now, closed path just now? Because we have a result here. If the line integral is independent of path, okay, if and only if for every closed path, the line integral is 0. Okay, what does this mean? Okay, so this means that, so the left-hand side, you know this. So any curve, for any closed path, okay, any closed path, okay, you integrate, you get the same number. Okay. The second one is that same number you will get is 0. Okay, so let me put down this word. Is independent of path. Okay. If and only if this line integral is 0. Okay. So when we talk about line integral, we need to talk about what curve, what path you take. Okay, what path you take. So the path you take here is closed path. So what does closed path mean? Definition of closed path. The terminal point coincide with the initial point. Okay, start and end at the same point. Okay, closed path. Okay or not? Hello? Understand the statement? Can understand the statement? Don't know how to prove it's okay, but you need to understand the statement. Okay. Okay, so there are two directions here. So one is independent, one is evaluate to 0. Okay, the other is you need to evaluate to 0 and then prove that the line integral is independent of path. And let me use this shorthand notation here. Okay, so there are two directions here. Okay, so what to do? So what to do? Can you do? Yeah, so what can you do? So actually this C here, right? This C here is not the same C here. Okay. So this independent of path, right? It's not just closed path, it's any path. Okay, so maybe I should maybe change this to D better. So this is a path. Okay, what I mean here is path connecting different A and B. Okay. Okay, connecting different A and B. Connect path connecting per possibly connecting. Okay. Okay. So if it is independent of path, why when you integrate over a closed path you get 0? Fundamental theorem of line integral. Do you have conservative vector field here? All right. Not sure. Okay. Not sure. If yes, then you can use fundamental theorem of line integral. But now not sure. Okay. Okay. So what we can do here is we need to. Okay. So this is proof for all closed path, right? So you need to pick one closed path first.
Okay, let's pick one. Maybe we pick this one here. Okay, pick this one closed path here. Okay, so let's try compute this. So what we can do here is we split the closed path into two parts. Okay, split into two parts. Okay, so call it A and B, 2 points here. I split into two lines. Okay, later we'll see why this will work. Okay, so we split into two lines. So we have integrating C1 F dr plus integrating C2 F dr. Okay, so not that we have an orientation for our curve. Okay, so we have this orientation A to B and then B to A. Okay, C1 and C2. Is it okay? Okay. So you can see that C1, what's the endpoint from where to where? C1 is from where to where? A to B. Okay, C1 is A to B. C2 is where to where? B to A. Okay, so do they have the same starting point and end point or not? No, I mean real starting point and end point. No, right? One start at A, one start at B. So can you do something to change so that their starting point and end point is the same? Minus, okay? We can introduce an orientation. Okay, maybe we'll introduce an orientation into C2. So if I change the orientation, what happened? You get a minus sign, okay, of C2 minus C2 of F dr. Okay, now this is a path from A to B, and then this is a path from A to B as well. Okay, but the condition of this integral is what? F, the line integral of F is independent of path. Okay, so it's independent of path. What's the definition of independent of path? Karen, what's the definition of independent of path? Yes. Yes. Okay, so between any 2 points, you take any path, you get the same value. Okay, so you see, in particular, C1 and minus C2 are the path from A to B. So they have the same value. So you take one value minus the same value, what do you get? 0. Okay, so you get 0. So you get 0. Okay. So you get 0 by assumption. And so here you change the line orientation. Okay, so this is one direction. How about the other direction? The other direction, you also do the similar trick. Okay, you also do a similar trick. So I left you the other direction, just left for exercise. So you just do the things backward. And for the other direction, you do things backward, and then you will see the result. Okay. Yeah. Next. Okay. So we come back to this theorem here. So we have proved one direction. How about the other direction? What's the other direction talking about? If it is independent of D, then you found that actually this vector field is a gradient of some scalar field. Okay, this thing is actually very important in physics, right? Because what they do is they have some vector field. Okay, they compute some line integral. Okay, but they see why if I take two starting point and end point the same, and I measure along different path, I always get the same answer. Why? It is because this vector field is come from a gradient of a scalar field. Okay, so this is the direction from 1 to 2. Okay, So because they do experiment, they measure the value. Why is it always the same? Okay, why is it always the same? Okay, because the vector field is a gradient of some scalar field. You will always get this result. Okay, so how do you prove this? So I briefly say it, I won't write down. So what can you do is you can consider two kind of path here. Okay, one path is when you start with the starting point, okay, you go up until you reach a horizontal level with the endpoint. Okay, and then you move horizontally. Okay, so what am I doing here? Okay, so maybe let me write something down here. Yeah, wait. Let me see. Okay, so if to prove two, right? To prove, okay, assume one. So to prove two, what do I do? What do I need to do? I need to find that. I need to find the little f. Okay, so I need to define. So to prove that, we want to show f is equals to del f for some f. So we need to define what is our f. Okay, we need to define what is our f. So how do we define it? Okay, so one way to define it is to define it as a integral. Okay, so how do I define it as an integral? So what do I do? So I define it as a two integral here. Okay, let me show you some computation, some idea. Okay, maybe you ask, why do we need these two integral here? All right. So why we define my f like this? Okay. So first of all, do you think that this is a function or not? Do you think this is a function? Is this a function or not? You don't quite see it yet. Okay, because there's no xy variable here. Okay, let me write one more. So there's no xy variable here. Okay. So let's go on. So how I introduce this xy here? So what I do is I first integrate from the starting point AB to x1 y f dr to integrate from xy x1 y xy. Okay, so what's the relation? What's AB here? Okay, so let me write here. So RT. So let me write here. So RT here is a path from AB to x1. Okay. And then we choose x1 less than x. Okay. So what I do is I choose this path. Okay. If you don't understand this definition first, it's okay. But what I do is I have a starting point, I have an end point. Okay. What I do is I pick a path that is at the end of this path, it is horizontal. This is what I did. Okay. Yeah, at the end of the path, it is horizontal. Okay, and then the mathematical terms is this. Okay, so I fix my y constant. Does it make sense? Make sense or not? Okay. Okay. So what's the benefit of doing this? What's the benefit of doing this? Okay, what's the benefit of doing this? So let's say if I differentiate this equation here, okay, I differentiate this equation with respect to x. What do I get? Okay, so the first term here is some constant. Okay, the first term here is some constant. Okay. Okay. Because xy I fixed already. Okay, so this is a constant. So here we will get 0. Okay, how about the second term here? Okay, so what's this second term here? I need to differentiate an integral. Okay, from x1, y to xy, fx. Okay. So what's this term here? This is a word done, right? Word done. Okay, word done. So this curve here is horizontal. So there's no change in y. Okay. So you can just make it into a line integral with respect to x. Okay. So you make it into a line integral with respect to x. And you make it a line integral of x. And then what's this? You differentiate an integral. So what you get is just you're differentiating an antiderivative. So you just get a derivative, which is f1, x1. Okay. So what I do is I just show one of the component of the gradient of my f is f1x. Okay, if I define f like this. Okay. Not okay. No okay. No okay. Okay or not? So what I do is I define this function here, and then I check that the first derivative of this function is f1x. So meaning what? Meaning what I have done here is I have del f, okay, xy, okay. The first part is f1, okay. What I want to achieve is second part is f2, so that I can write f as a del of scalar field. Make sense or not? So this is what I haven't done. I need this so that I can say that my f is equals to del f. Make sense? Yeah, so it makes sense. So I mean, to find del f del y, you need to pick a different path. Yeah, you need to define your f with different path so that you have similar trick here. One of them is 0, the other what you get is f2. Okay, but you can see that my fxy seems like define it different way. But your condition is what? The integral is with respect to path. So no matter how you change the definition of this integral here, they should give the same f. Okay. Okay, I will write the full things out in the notes, and then you can check. Okay. So the other direction is given by this picture. Yeah. Yeah. Question. Yes. 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 Definitely. Definitely. Yeah. Definitely. Yeah. In 3. Yeah. Yeah. Definitely. Yeah. In higher dimensional, you can just generalize this proof. Generalize this proof. So you keep constant in the other two directions and then find one direction. Okay. Okay. I mean, this proof is showing you how powerful is independent of path. Line integral is independent of path. And then you need to know the technique of integration, word done integration, and then how to differentiate the integral. Okay, so these 3 pieces put together, you can get this result. Okay. 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 Let's go on first. So the summary is the function, okay, let's say it is conservative. That means that it is independent of path, okay, which is also equivalent to you integrate any closed path, you will get 0. Okay, so these are all equivalent. Okay, so 1 implies 2, 2 implies 3, 3 implies 1. So you can jump 1 to 3, 2 to 1, 3 to 1, and so on. Okay, so these are all equivalents. Okay, so when people tells you I have a conservative vector field, okay, then you should know that my line integral is independent of path. And if I do line integral on closed path, I always get 0. Okay, so if you go up and go back, that means you did nothing. Yeah, you did nothing. So the word time is 0. Okay, although you already like go around the globe, you still did nothing. Okay, yeah. Okay, next new concept here. So simple curve. So a curve that does not intersect itself anywhere between its endpoint. Okay. So actually, one way to see it, yeah. So you can see that this example here. So first one is simple, not close, and then the other one is not simple, not close. Okay, not close because they are not joined. So the endpoint and the starting point are not joined. Why is it not simple? Because it intersects self-intersecting. Okay. So there's one criteria I remember my lecturer told us, also in vector calculus. I'm not sure it's equivalent or not. I forgot already. But he says something like, if it is a simple closed curve, you can draw a line between any 2 points without intersecting the curve. Okay, so if it is a simple closed curve, you can draw a line between 2 curves, okay, between 2 points in the curve, but doesn't intersect the any point in the curve. Okay, for example, this is not simple and close. Okay, for example, if I pick the 2 points here and then I draw a line, then I will intersect the curve. Okay, every 2 points. Yeah, every 2 points. Every 2 points. Okay, so you don't want self-intersecting. Okay, so you cannot flip your. Because why? Because if you intersect here, right, this is not injective anymore. You can think that this curve is not injective. If you think of this curve as a function, you can see that there are 2 points get sent to the same point. They're not simple anymore. It's not injective. Okay. Next is the simply connected domain. So a simply connected domain is a connected domain where one can continuously string any single closed curve into a point while remaining in the domain. Okay, so simply connected domain, you can string into any single closed curve into a point. Okay, so you can string. For example, this is a simply connected domain. Why? Because you can string it into a point. Yeah, this is a topology already. So if you think about, I talked about line connecting 2 points, right? Okay, you can think of this line string, right? So between these 2 lines, I can string this line. Okay, I can string it. So you can see that these 2 lines these 2 points get closer and closer. So I'll draw something. This. Okay, let's say I string until this. Okay, so you can, if you can continuously string into a point, then it is a simply connected region. Okay, so for example, these 3 are not simply connected. Okay, why? For example, this one here. Okay, do you know what it can string to? Don't know. So you see, so here is the space that you can string. Okay, so how to think of this stringing? So you can think of this, we call it a stratification, or you can think of this, how to break up this space here. And then you try to string this vertical line here. Can you imagine or not? Can you imagine? So let me draw something. So you start with this, and then you string, and then you string, and then you string. Okay, or the other case, you also can string upward. Okay, so what do you think it can shrink to? Just a circle, right? Just a simple closed curve. Right? Either the inner one, either the outer one. Correct or not? So the outer one can shrink into the inner one. Okay, and then the inner one can expand to the outer one through this space here. Does it make sense? So you imagine because this is simply connected, right? So within this is simply connected, so you can draw lines. Okay, so you imagine like you're putting a kite, right? A kite. So you are holding the kite here. Maybe here is the kite. So you what? you How do you play kite? What do you do when you play kite? Shuffle. Shuffle. So I mean, when you extend the length, when you extend the string, what do you call that action? When you play the kite, you know kite? Yeah. So when you extend the string, what do you call it? Huh? What do you call it? Don't know. Yeah. What? Huh? Rolling. REEL. Rolling. I mean, there are two action, right? You can extend the string and then so both or reeling in or reeling out. Okay, so if reeling in, then it's like decreasing the length, but reeling out is increasing the length. Okay, so you can think of this line here. Either you decrease this line or increase this line. Okay, so if you stay here and then decrease it, then this outer circle here will get dragged into the inner circle. Okay, if you stay outside at the outside circle here, and then you try to reduce the length, then the inner circle will go to the outer circle. Make sense? It makes sense? Okay? Yeah. Mm. Yes. So any simple closed curve, especially the boundary, right? Especially the boundary. So anything inside here, any so here. So let me highlight the word you're talking about. So you say any simple closed curve. So in particular, the boundary is also a simple closed curve. Boundary doesn't change. No. I mean, okay. Okay, let's read about this definition again. So what's the object here? So the object here is a domain. Okay. The adjective here is simply connected. So what's the simply connected domain? You need to start with a connected domain first. Okay, connected domain first, where one can continuously string any single closed curve into a point. Okay, so you need to able to string any closed curve into a point. Okay, but what I said just now is there are curves for this example here. There are curves that you cannot string into a point. Okay, for example, the outer one you can only string into the inner circle at most, or the inner one can string to the outer circle at most. That's all I say. It doesn't string into a point, so it violates the definition because you need to string any simple closed curve into a point. Mm. Yeah. Any question? Youngzi? Yeah. Mm. Or you think that this definition also not specific, is it? Seems like not too specific. Yeah. Any other question or not? Other question? Okay. I mean, in this course, we won't test you whether something is simply connected or not, but we will use this condition to apply some theorem. Okay. Yeah. Question. How do you string the second one? This one. This one. How do you string? I mean, depend on what you want to string. What do you want to string? If you want to string this curve here, then you only can string up to something like this. Right. The middle is a line. You mean can I join them? Oh, okay. I think you mean something like this. Yeah. You mean like this, right? Yeah. 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 Mm. Mm-hmm. Yeah.
And the third one become 2 points, right?
This actually is simple but not connected. This is not connected. This is simple. These two are simple but not connected. So it is not simply connected. The last one is not connected, so it's not simply connected. But if you look at individual connected component, we call it connected component, then they are simple connected. Make sense or not? If you look at one of this, we call it connected component. So this is a simple connected. If you look at the other one, also simple connected. But if you put two together, it is not connected. So because simply connected need to start with a connected component diagram, but it's already not connected, so you don't need to consider anymore. Okay. Yeah. I mean, yeah, you guys should learn this topology, differential geometry, and then algebraic geometry to really make full use of your maths degree. Okay, otherwise it's just a normal degree, I think. Okay, so yeah, to work with me, right? Better know something like this. Otherwise, very hard. We need to form a team. Yeah, we got across different field and can discuss together using different tools. Can. Sure. Yeah. So make sure you learn algebraic geometry, topology, algebraic topology, differential geometry. Then you can work together. Huh? Financial? That one you can learn for your own use. It's okay. I don't care. You can learn for own use. Yeah. But yeah, for the other, you should learn. Yeah. Because otherwise you will never touch this thing again. Yeah, you won't touch this thing. Touch, then don't touch. Yeah. Okay. Wow. We haven't learned any calculation yet. Okay, so the result here is the theorem is if I have a vector field on an open simply connected domain, okay, and we also can compute continuous first order partial derivative on my f1 and f2, then the result is f1 f is conservative if and only if del of f1 del y is equals to del of f2 del x. Okay, so you can see that what is this? So my f is f1 and f2, right? f1 is in the x direction, f2 is in the y direction. But if I check the derivative at the opposite direction and they are equal, then my f is conservative. Okay, so this is another way to check whether f is conservative or not. Because the definition is what? What is the conservative vector field? What's the definition of conservative vector field? It is a gradient of a scalar function. Okay, but to prove from definition, you want to find the scalar function. Okay, in general, is it easy to find the scalar function? Okay. Or just now, what do we have? The line integral is independent of all paths. Can you compute all paths or not? Okay, what's the all path computing? There's a very famous in physics one. It's the Feynman integral. Okay, when they do the quantum physics, they need to integrate all paths. Okay, so this one independent of all paths. So you need to check all the paths. Is it possible to do that or not? How many paths you need to check? Infinitely many paths you need to check. Okay, but this give a easy criteria. You go to your vector field, okay? Take f1, do partial derivative on y. Take f2, do partial derivative on x. They equal or not? If they're equal, then it is conservative. Because this is if and only if. Okay? If it is conservative, this equation must hold. If this equation holds, it has to be conservative. Okay. Okay. Hey, can you guys stay a little bit longer? Or can you guys stay a little bit longer? Can okay. If you want to leave, then you leave. Okay. Let's talk a few more theory first. Okay. Okay. So this one done. So we won't prove it. Okay. So extend to tree space. How many things you need to check? Okay. So into tree space, you need to check three things. Okay. Del of f1 over del of f del y equals to del of f2 del x. Del of f1 del z equals to del f3 del x. And then del of f2 del z equals to del of f3 del y. So you only need to check three of them. Okay. And in principle, there's more, right? I think there are more to check, but I guess they reduce it to these three here. I think the others should be implied. Okay, so they reduce to this three condition here. Okay, so let me see here. Okay, let's do one example. Okay, let's do one example. Let's show this. Okay, show that this f is conservative. Okay, so hence find f such that f equals to del f. Okay, good. So now you want to show that it is conservative. Okay, so what do we do? So we need to check that. What's the condition just now last we get? f1 over del f1 over del y equals to del f2 over del x, del f1 over del z equals to del f3 over del x, and then del f2 over del z equals to del f3 over del y. Okay, so we need to check these three things to check whether it is conservative or not. Okay, so so what? So we just compute it. So let's compute it. So what is del f1 del y? Okay, so this is just minus ex sine y on z. Okay, and then del f1 with respect to del z is y, and then del f2 with respect to del z is x, and then del f2 with respect to x is sec minus ex sine y, del f3 over del x is y, and then del f3 is x. Okay. Okay, so from here, you can see that the three equation form. Okay, so you can see that the three equation form. So if you want, you should check whether I compute the right derivative or not. Okay. Okay, but the theorem only hold in open simply connected set, right? Okay, open simply connected set. So here, this function, this vector field here, hold in what space? This is a vector field from where to where? This vector field from vector field on where? Yes, so it's a function from R3 to R3. So is R3 open simply connected or not? You string any closed curve, simple closed curve to a point. You can, right? Okay, because there's no hole in R3. Okay, in particular Rn, all the n. Then you can string all the simple closed curve into a point. Okay. Yeah, so this one done, this one done. Okay, so f is conservative. Okay. But the problem here, this is the problem. The problem is you want to find the scalar field. How to find a scalar field? How to find a scalar field? You know the derivative. How to find the f? Integral. Okay, you do integral, right? So you do integral. So let me write out something here. Okay, you do the integral. So, okay, so you do the integral. So f in this case here is what? Is del f of del x, del f of del y, del f of del z. Okay, so what are these? So these are the given function. Okay, so these are given. So you have three equations here. Okay, you get three equations here. So I think you should be quite reminiscing, right? So you want to solve this. How to solve this? You need to integrate. Okay. So what do you integrate to? So for example, the first one. Okay. If I integrate this, what do I get? What function do I get? Okay, I get e to the x cos y plus xyz plus some function in yz. Okay. Correct. Because if I differentiate the function in yz, it will disappear in this derivative. Make sense? Okay. And then I integrate with respect to x for the rest. Okay. So what's the next condition here? So you want the second equation to hold. Okay. But you only found the new presentation for f. So you need to differentiate your f with respect to y. Right? Okay, and then you compare them. So you differentiate your f. So let me write down x, y, z here with respect to y. Okay, what do you get? You get minus ex sine y plus xz plus gy yz. Okay, and then you want this to be equal to the second component here. Right? Okay, so you need to compare these two. So you want to make them equal. So this should be equal to xz minus ex sine y. Okay, this implies what? What does this imply? That this implies that my gy must be 0. Okay, so my gy must be 0. So if my gy is 0, what does this imply? Huh? G differentiate with respect to Y is 0, meaning what? Differentiate with respect to Y is 0, meaning what? Meaning my G has nothing in Y, okay, or a constant in Y. Okay, so this means this is a function entirely in Z. Okay, and then you repeat the process. Okay, you repeat the process. So you repeat the process. So what do I get? So let's call this H. So you repeat the process. So I substitute it in. So I found out that my G is actually something in Z. Okay, and then we repeat the process for the third one. And then we differentiate this again with respect to Z. And then we want it to be equal to the last component xy. Okay. So in this case here, what does this mean? My h prime z is also 0. Okay. So if you have no change in z direction, what does it mean? You are actually a constant function. Okay. So you're actually a constant function. So we don't have an initial condition, so we can just leave the answer with a constant. Okay. Okay. So far, so good. And can we finish green theorems and then we go? But if you need to leave earlier, then you leave. Is it okay? Yeah. So let's stop. Let's do green theorems and then we finish today. Okay. 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 If you need to leave, then you leave. Okay. Okay. So next. So the idea of conservation of why do we call this kind of field conservative? Okay, because the idea is from this conservation of energy, because you can see that you can get the vector field, okay, out of the potential energy. Okay, you can obtain the vector field from the potential energy. But if you obtain the vector field from this way, okay, you can see that the force field have to satisfy conservation of energy. Okay, the conservation of energy here means you remember, so you throw a ball, right? Okay, your ball start with a potential energy. You throw it up, the kinetic energy increase until and then decrease until stop at a potential energy, and then when it drop, and then turn to kinetic energy and then reduce the potential energy. Okay, so this whole process has to satisfy conservation of energy. Okay, so if you obtain your force field, they should satisfy. Obtain a force field from this potential energy, then they should satisfy this conservation of energy. So that's why we call those force field are conservative. Okay, because they usually come from this special scalar field here. Okay, next. Next is this green theorem here. So before we talk about green theorem, so let's talk about this orientation. So the positive orientation of a simple closed curve refer to a single counterclockwise traversal of C. Okay, so when we talk about orientation, right, we usually say that counterclockwise is positive orientation. Why? Because this is the same as how we build our coordinate system, right? So why? Do you wonder why? Why not we draw x downward, y downward? Okay, why we always draw x like this, y like this? Okay, why not we draw y downward? Okay, because this is our convention. This is anti-clockwise. Okay, we add anti-clockwise. Okay, so 3D we add the right hand grid rule. Okay, if I'm not wrong, right hand grid rule. Okay, we use the right hand grid rule to add the extra axis. Right. So we have x. Okay, we have y, and then my z must go up, not going down. Okay, so this is the positive orientation we are talking about. Okay. Yeah. So how about negative? Then negative, that means you are going clockwise. Okay. So this is the orientation of curve. Okay. So when we say positive, then it is anti-clockwise. Negative, then clockwise. Okay. Okay. So next, Green's theorem. So let's see be a positive oriented piecewise smooth simple closed curve. Wow, every adjective already get used up. That forms the boundary of a region D in XY plane. Okay, so here meaning what? Here, this green currents here, we only restrict to R2. Okay, XY plane, just R2. So a region in R2 is a surface. Okay, so the boundary of a surface is a line. Okay, so if it is closed, then we get a closed line, closed curve. Next, what's the statement here? So if Px, Pq have continuous partial derivative, so when the statement start with this, right, that means this theorem must somehow use this continuous partial derivative. So let's see how we use this partial derivative. So if PQ have continuous partial derivative on the open region that contains D, okay, the D bounded, what is D? D is the region bounded by the positive oriented piecewise smooth simple closed curve, then the following equation hold. Okay, the following equation hold. So you can see that inside this equation, we have to compute what is the partial derivative. Okay, and then we take the difference. Okay, we take the difference. So del Q, del X, del P minus del P over del Y. Okay. At the moment here, this Q and P, the order doesn't matter, right? But on the right hand side here will denote what happened. Why? Because on the right hand side here, P come with dx, Q come with dy. Okay, so you should notice that, you see. So on the right hand side here, P dx, but on the left hand side here is partial derivative with respect to y. So it's opposite. Can you see? Can you see the difference now? Okay. Okay. So on the right hand side here, integrate P dx plus Q dy, but on the left hand side, you care about del Q del X and del P del Y. Okay, so you need to remember the order here. Okay, don't swap the order. Okay, so left hand side here is what? It's a multiple integral. It's a double integral. But on the right hand side here is a line integral. Okay, so you reduce a multiple integral problem to a line integral, or you can compute a line integral using a multiple integral. Okay, so what does this mean? So you should imagine some picture like this. So you have a C. Okay, you have a C, and then here is the region D. Okay, suppose if you want to differentiate some function above the D, okay, it's equivalent. Okay, it's equivalent to integrate over just the boundary. Okay, or if you want to integrate over the boundary, it's equivalent to integrate over the surface. Okay, but make sure that you know what happened inside here. What's the function you use here? Okay, what's the function you use here? So you notice what is this? What's this here? Does this look similar to anything or not? Does this look similar to anything? Huh? Fundamental, not quite. Not quite. What's the object? What's the object? Yeah, separating. So you can think of it. One example it can be used is the word done, right? So when you calculate the word done, you can split into dx dy component. Okay, so you can think of this PR Q as a component of your vector field. Makes sense or not? Does it make sense? Okay, so you can think of this TQ as a component of your vector field. All right. Okay, so there's a fancy way to write down the line integral. Okay, we put a circle here. this line integral. So what's this fancy line integral means? It means that you integrate with the positive orientation. Okay, positive orientation. So if this path is not closed, right, there's no positive and negative to talk about. Okay, so it also makes sense why we draw a circle there, because this C here always represent a loop. Okay, always represent a closed curve. Sometimes we call the closed curve as loop. So once you have a loop closed curve, then you can go either counterclockwise or anti-clockwise. Okay, so it makes sense. Yeah, so whenever we talk about, so when you see this notation here, so this is a closed loop. Okay, closed loop. And then we choose the positive orientation. Okay, so this is the convention. Okay, another notation is because this curve bound a surface we call D. Sometimes we also use del D. Okay, del D. Del D here is the boundary of D. Okay, so in this, for example, C here is the boundary of the D. Okay, so in this example here, okay, del D is a notation we use for boundary point. Okay, so far okay. So far okay. Jimbo looks dead. No? Okay. Okay, next, let's see how we use this example, use this theorem, okay? So let's see be the boundary of the triangle, again, vertices with these three vertex, 0, 0, 1, 2, and 0, 2. Calculate the line integral, okay, for x squared y dx plus 2y dy. Okay, so so this notation here is integrate over a closed loop with what orientation? 原价. What's the orientation we choose to integrate this closed loop? Positive or negative? Positive or negative? Positive. Okay, we always choose positive. So positive is going anti-clockwise. Okay, so this is the notation here. I mean the diagram here. So to do line integral, right? Okay, what do you need to do? You need to parameterize the curve. Okay, parameterize the curve. So how to parameterize the curve? So we split this curve into C1, C2, C3. So what is the line C1? You know? How do you find this line equation here? Connecting 0, 0, and 1, 2. Y equals to 2x. Okay, good. So my x is going from 0 to 1. How about C2? Y equals to 2 because my y is constant. And then my x is going from where to where? 1 to 0. So here you need to take your range following your orientation. Okay, otherwise you need to introduce a minus to your integral. How about C3? X equals 0. Okay, good, very good. So the orientation here is 2 to 0. Okay, so this line integral here, how do we compute this line integral? Okay, if you are not familiar with this line integral here, actually this is just the normal line integral. But we just say that it is closed loop, so we draw a circle there. So how do we compute this line integral with respect to x and y? Means you. What? So here is what? Here x equals to x. Okay. Any different derivative or not? What's the derivative? X prime x is just 1. Okay, so the extra contribution is just 1. Okay, 1 dx. Okay, x is going from where to where? 0 to 1. Okay, How about y? Sorry, not y. So not y. I mean the second function here. 2 times 2x. Okay. 2 times 2x. How about y prime x? 2. Okay, so you will have a contribution 2. Okay, and then dx. Right? We changed variable to x already. Okay. So if you are confused, right? Okay, if you are confused, what did I say last time? Change all the s to t. Okay, then you won't confuse anymore. Okay, so don't confuse with this, the previous x and the next x. Okay? So if you change notation to t, so t, so let me notation here. So x equals to t, y equals to 2t, then x prime t is just 1, y prime t is 2. Okay, then you change everything to t. Also works. Okay, they are equivalent. So what I want to try to emphasize here is the 2x here is different. Okay, the x here and the x here is different. Okay, it's a different x. Okay, first x is a function, the other s is a parameter. Okay, so because you are a mathematics degree, right, you should be able to discern this kind of thing. Okay, so why some lecturer will always write typo, write wrong? Because in their mind is the other thing. Okay, so sometimes they will write typo. So you need to know what they are thinking. So to know what they think, you need to ask. Okay. Okay. Yeah. So yeah. Yeah. So you need to. This is one of the skill you need to differentiate all these variables. Okay. Next. So on C2. On C2. On C2, you integrate from 1 to 0. Okay, 1 to 0. Also for x squared times 2. Okay, so the contribution from x is 1 also. Dx plus 2 times. Okay, so the contribution from y is what on C2? Y. What's the derivative from y on C2? Any change in y or not on C2? What is y prime? Yeah, y prime. Any change in y? No. Okay, so y prime is 0. Okay, because y is also is a constant. So you differentiate a constant, you get 0. Okay. Okay. Okay, you keep going. So you apply the same thing. Okay, same thing. So here is even easier for this one because x is already 0. Okay, so your function contains x. Yeah. So this term is 0. How about next term? What is y? Y is y itself. Okay. So you get 2y dy. So we write things in y. Y equals to y. Okay. Okay. Question? Which one? 2y times 1. This one. This one, 2y times 1. All right, a 1 there. You mean there's a 1 here. Yeah. Okay, yeah. Sure. Yeah. Yeah. Okay. So you integrate everything here. What do you get? Do you get anything? Oh, let me write down the term first. Yeah. Try check. What do you get? See Jingbo go get the same answer. Same answer. Okay. -2/3. Okay. Yeah, so we got -2/3 here. So how about the other way? Okay, how about the other way? Okay, let's solve it using multiple integral technique. Okay, through Green's theorem. Okay, why can we use Green's theorem here? Because this is a simply connected. So let's try this Green theorem, then we can leave for the day. Okay, so what's the Green theorem statement here? Del Q del X minus del P over del Y of EA equals this line integral CP dx plus Q dy. Okay, so you need to identify what is P and Q in this case here. Okay, what is our P and Q in this case? What's our P? 4x squared times y. What is Q? Huh? Y. Okay, so have we satisfied the condition in our theorem or not? So this curve is positive oriented. Okay, good. Piecewise smooth. Okay, just straight line. Simply closed curve because it's closed. Simply simple because you can contract. Okay, between them. Okay, so let's do this. So what is del P del Y? So del P del Y is x squared, 4x squared. Del Q del X is just 0. Okay, so our line, our multiple integral become 0 minus 4x squared of EA. Okay, so become the multiple integral question. Okay, so how to integrate this domain here? How to integrate a multiple integral? Vinny's theorem. Del x del y or del y del x? Del y del x. Okay, let's pick del y del x. So meaning we need to fix x first and then fix y. Okay, so x is going from where to where? X is going from 0 to 1. Okay, we fix x from 0 to 1. But how does my y change when I fix x from 0 to 1? How my y change? Bounded above and below by what? Bounded below by C1. Okay, bounded above by C2. Okay, so what is C1? C1 is 2x. Okay. C2 is so let's write down this integral here from 0 to 1 and then 2x to 2. Okay, good. So what is this integral here? So we got, because there's no y, right? So you can just introduce a y variable in, and then we get 2 minus 2x dx. Okay. And then minus nx squared plus nx cubed dx. And then what's this? What is this? You finished compute already? Okay, so for the theorems to be true, this has to be -2/3. Okay. Yeah, so you can compute, you can try and compute the integral, you should get -2/3. Okay, so we stop at green theorems and then we will continue next time. I think we have half of the content, I think should be okay. Okay. We will do maybe one more example for green theorem next time and then continue. You can try the example first at home. Okay, then I will pick 1 and 2 next time. Okay, so see you next time, next Wednesday. Hey, sorry. Sorry, I forget to check attendance. Yeah. Okay, Summer is here. See if you heard your name or not. Yu, Sun Ling, Kai Ren, Jingbo, Jingbo not here. Wai Ying, Pishon, Ying Qi, He Yi, Xue Yan, Jiang Chen, Jia Ye not here, right? Li Kai not here. Yuan Jia, Wen Suo, Yiding not here, right? Just now I didn't see it. Yu Wei, Yan Bo, Chen Ye, Lin Jing not here. Dong Jie, Yu Jing, Jing Yu not here. Liu Qing, Zheng Cheng, Suo Ning, Wu Li, Tian Jing not here. Ziqian, Ze Xuan not here. Ling Ying not here. Grace here. Syed here. Jia Wen, Ming Xiu, Michelle, Ryan, Ellie, Yongzi, Xuan not here. Okay. Huh? Still, yeah. Okay.
What this is should be an open, simply connected domain. What is an open, simply connected domain? Just use the open set.
Yeah, just use open set.
But it should be simply connected.
Yes.
For example, this not contain all the boundary point. Maybe this one.
If this is if you throw away this boundary, then it's open.
This is
Yeah.
oh.
If you throw away the boundary, it is open.
So we use piecewise